Okay, so this is the final lesson of the indices and surds topic, and it's called exponential equations. And it's kind of one of those areas where it's up to the school whether or not we teach this. It's something that's considered extra in the curriculum. So if you don't get this, it's probably not going to be heavily examined. But I don't think it's all that hard. It's just a different way of thinking about equations. So we would have already done linear equations. So you're thinking of your y equals mx plus b, and that's these guys here. And then we've already done quadratic equations, which is where we've got x to the power of 2. Exponential equations are just a different type of equation where our unknown, our x, is in the index, is in the power. It's not, so like in this particular case here, there's 2 to the power of x. And they're not altogether all that hard. If we think about it, let's think about the number 8. How can we write the number 8? Well, we can write the number 8 as 2 times 2 times 2, because 2 times 2 is 4, times 2 again is 8, which we can also write as 2 to the power of 3. So in other words, if we had said 2 to the power of x equals 8, well, the only possible answer to that is 3. 2 to the power of 3 is 8. And we're using that basic sort of way of doing things, except with an exponential equation, what we're probably going to do is we're going to say, well, 2 to the power of x equals, well, let's see if we can change 8 to have the same base as the base below x, and then we can work things out. So we would say, well, 8 expressed as 2 to the power of something would be 2 to the power of 3. So if 2 to the power of x equals 2 to the power of 3, then the only possible way that that statement can be true is if x equals 3. Okay? And that's basically how we run it. So we're just trying to get things to the same base. And so here's our basic rule. So if a to the power of x equals a to the power of y, then x must equal y. Otherwise, this isn't going to hold true. This equal sign in the middle is not going to hold true unless those two powers are the same, assuming we've got the same base. Of course, in some examples, we won't have the same base. And so this is what we have here in the very first example. Example 1, 2 to the power of x equals 16. Well, let's first think, well, what's 16 expressed in terms of a base of 2 to some power? So 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. So 16 is just equals 2 to the power of 4. So therefore, for 2 to the power of x to equal 2 to the power of 4, the only possible way that's going to happen is if x equals 4. Otherwise, any other number you put there for x, if you substitute in any value in the world for x there, aside from 4, you're not going to get the right answer. Okay, so now we start throwing in a little bit of stuff that we try to sort of understand through this indices topic. And so we've got 3 to the power of x equals 1 over 9. And your initial thought might be, oh, hang on a second, how am I going to get that into the form of 3 to the power of something? But remember, 3 to the power of negative 1 was 1 over 3, wasn't it? And we learnt that a little while ago. And so really, 1/9 just equals 3 to the power of negative 2. So 1 over 3 squared. Because 3 times 3 is 9. So essentially what we've got is 3 to the power of x equals 3 to the negative 2. Because 1/9 equals 3 to the negative 2. That means x must equal negative 2. Otherwise that statement's not going to hold true. Now in the next case, we've got a situation there where we've got 25 to the power of x equals 125. Now if I put 25 to any integer power, it's going to go well past 125. Just to demonstrate that, there's my calculator there. So just 25 squared is going to get us well up to 625, so that's way too far. But then 25 is itself a square number. Another way to write 25 is to say, well, 25, that just equals 5 squared. So what we've actually got there is 5 squared to the power of x equals, now 125, isn't that 5 cubed? Let's just have a look. What does 5 cubed equal? It does equal 125, so that just equals, so 125 is just 5 to the power of 3. I might just write that here So 125 equals 5 to the power of 3. So now that we know that 5 to the power of 2 then to the power of x is equal to 5 to the power of 3. So let's just deal with our usual index laws here, and when we have a power to a power we multiply, so it's going to be 5 to the 2x equals 5 to the 3, which means that for the only way this is going to hold true is if 2 times by x equals 3, which means that x equals 3 divided by 2. I divided both sides by 2. Okay? So we just got to get them in the form that we've got. I'm sorry, I'll just get a highlighter here. We want to get the whole thing simplified to that first. We want to get it to a situation where we've got both sides expressed with the same base. And then from there we can start to work out exactly how we're going to work out the value for our pronumeral. So these next ones get a little bit more tricky. So we've got 3 to the power of 2x minus 1 equals 27 to the power of x. So the very first thing we're going to do is let's get the bases the same. I'm not going to be able to change 3 to the power of 2x minus 1, but 27, well, that's just 3 cubed, isn't it? 3 times 3 is 9, times 3 again, that's 27. So therefore we're going to have 3 to the 2x minus 1 equals 3 to the 3 to the power of x. And if we simplify that, we're going to have 3 to the 2x minus 1 equals 3 to the 3x. So the only way that's going to be true is if 2x minus 1 equals 3x. Otherwise, we're not going to get a possible solution to that question. So if I start next by taking away 2x from both sides, I'm going to end up with negative 1 equals x. And there's my answer, x equals negative 1. Okay, moving on to the next one here. Once again, we know that 49 is just 7 to the power of 2. 7 squared is 49. So therefore, 7 to the 3x minus 4 equals 7 squared to the power of x. So we simplify that again. 7 to the 3x minus 4 equals 7 to the 2x. And for that to be true, then obviously 3x minus 4 has to equal 2x. Otherwise, this whole equal sign in the middle is going to fail. So we go 3x minus 4 must equal 2x. It's the only possible way to get a solution for that one. And if in this one, I might actually take away 2x from both sides. So I'll end up with x minus 4 equals 0. And then I'll add 4 to both sides, and I'm going to end up with x equals 4. All right, so I've just paused there because I had a little bit of a technical difficulty, but we'll come back now. So let's think about what that means, and let's just see if that makes sense. In this particular case, we say x equals 4. So that means, if x equals 4, then 3x minus 4, which is the power that 7 is put to, is going to be 3 times 4, that's 12. 12 minus 4, so that's going to be 8. So what we're saying is 7 to the power of 8 equals, or actually I'll just hold on there. And on the other side, sorry, we've got x equals 4. So what we're saying, is 7 to the power of 8 must equal 49 to the power of 4. Which does kind of make sense, but we can just double check that with our calculator if we want to. So if I had 7 to the power of 8, that's going to equal that number. Now if I just copy that down, capture my screen and I paste it down here. And we can just check that against now going 49 to the power of 4. And there we go. So the two numbers are exactly the same. So what we've done must work because when x does equal 4, those two numbers both equal 5,764,801. Okay, so it takes a little bit of, it's not particularly difficult. We just have to get used to this idea of try and find the correct base. Once I've got the two bases the same, then I can say, well, whatever their powers are must equal each other. And from there I can solve the equation. So have a go at those ones. If you don't quite fully get it, that's okay. We'll be moving on to trigonometry next, and this won't be heavily examined if examined at all. But it's a nice little sort of precursor to some of the stuff that comes up in year 11 and 12, so it's worth having a crack at. And that's the end of today's lesson.